video, I will teach you the basic electronics as per the VTU syllabus. The first is the module 1, there the semiconductor devices and applications. In this present video, we are going to study about the semiconductors, types of semiconductors, PN junction, and the characteristics of the PN junction, and rest of the topics will be continued in the next video. So first we'll start with the introduction to this chapter. So here we are going to study with the semiconductor diodes and its applications. So first let's see what is a semiconductor. A semiconductor is an element with electrical properties between the conductors and an insulator. So when you say an electrical property, it is the conductivity of the element, and each of these atom, when you consider a semiconductor, the atom has 4 valence electrons. So here you can see with the figure which shows the atom of a semiconductor. So the main example or some of the examples are germanium and silicon. So considering a silicon atom, if we consider a silicon atom, it is having 4 valence electrons. So each of these valence electron will form the bonding with the adjacent atom to obtain its octet condition. So they form the covalent bonding, or they share the electrons between the atoms. And the figure here shows the energy band diagram of the semiconductor. So when you see over here, there is a valence band and a conduction band as shown, and the gap between the valence band and the conduction band is very small. So when you see to the insulator, the gap between this conduction band and the valence band will be very large, and in conductor it will be overlapping. So here there is a small band gap between the conduction band and the valence band. So in the valence band there are large amount of electrons, and in conduction band only few due to the temperature, and hence there will be a less conductivity in the semiconductor. So if the energy is supplied to the electrons in the valence band, they will jump into the conduction band, and there will be a large conduction in that material. Semiconductor in its pure form is called as an intrinsic semiconductor, and this is the band diagram for intrinsic semiconductor. So here we see that the valence band is completely full and conduction band is having few free electrons. At absolute zero temperature, the conduction band will be empty and the valence band will be completely filled, and it acts as an insulator. And at the room temperature, the valence electrons absorb the thermal energy, due to which they break the covalent bond and drift into the conduction band, resulting in conductivity. As the temperature increases, the conductivity of the semiconductor also increases due to the electron moving out from the covalent bonding. When an electron breaks out of the covalent bond and jumps into a conduction band, it results with a hole in the valence band. And hence, in a pure semiconductor, the number of holes and the free electrons will be equal. The conduction occurs in the material only when a voltage is applied across the semiconductor, which causes the motion of electrons and holes in a particular direction. The movement of electrons in a particular direction results in a current. So with the application of potential difference, we will have the conduction or the movement of the holes and electron in only one direction. So as we have both holes and electrons in the semiconductor, the free electrons, the electrons present in the conduction band, they tend to move towards the positive terminal. All the electrons move in a single direction towards the positive terminal, resulting in the electric current due to the electrons. In the same way, we also have the holes in the semiconductor, and these holes, as we know, they are present in the valence band. Okay, so when a free electron, if a free electron or an electron, as an example, when you consider here, there is a hole, the empty place is a hole. So in this case, an electron, when you say it jumps from the covalent bond at the point B, if you assume, or at A, it moves into this hole. A hole is generated in the point A, and next this hole A will be filled by one more electron, maybe from the point B, and from the point B, when it jumps into A, there results a hole in the point B. Similarly, the movement of the hole, when you see here, from C it falls into the B, C is vacant, and from D it falls into C, D will be vacant. So in turn we can see the hole is moving towards the negative terminal of the battery. So this proper movement results in the hole current. Hence the semiconductor is having both the current due to the free electrons and also the current due to the holes present in the semiconductor. Semiconductor. So as you know that in an intrinsic semiconductor, it is a pure semiconductor, and the electrons and the holes will be of same quantity or in same number. So in order to increase the conductivity, we need to have more number of electrons. So the electrical conductivity is increased by adding some impurity atoms. So these impurity atom will give us the electron and a hole. So that results in the higher conductivity. Then the process of adding an impurity atom is called as doping, and is called as an extrinsic semiconductor. So this extrinsic semiconductor, we can vary the conductivity by adding the impurity atom, and depends on the quantity of the impurity atoms we are going to add in. So due to the process of doping, we are having two kinds of extrinsic semiconductor. So that is an N-type semiconductor and a P-type semiconductor. Next, let's see what is an N-type semiconductor. So when you say an N-type semiconductor, it is formed by adding the pentavalent impurities, or also called as donor impurity. When you say an pentavalent impurity, this pentavalent impurity is going to have 5 valence electrons. So when this 5 valence electrons is added into the semiconductor, so as an example, for the pentavalent impurities as arsenic, phosphorus, lead, antimony, and so on. So when this atom, like arsenic, is added into a germanium, so germanium is a pure conductor. When you add to the germanium, you see that germanium is having 4 valence electrons and arsenic is having 5 valence electrons. So the 4 of the arsenic valence electron will combine or share, so that germanium atom and the arsenic will form the covalent bonding to have its octet state, and the one which is free will be left over inside the semiconductor. So the pentavalent impurity will give us one free electron. So as many free electrons are produced by the addition of pentavalent impurity, the thermal energy of the room temperature will generate say few electron pairs. So this, when you consider this point, due to the thermal energy, some of the electrons in the valence band will jump into the conduction band. So that results in a hole in the conduction band. So this hole electron pair will be generated along with the pentavalent impurity atom. And however, the number of free electrons produced by the pentavalent impurity will be more than that of the holes, and due to this dominance of electrons compared to the holes, this semiconductor is said to be the n-type semiconductor. And the current conduction in this n-type is only. Now let's see how the conductivity takes place in the n-type semiconductor. So as we know, when you apply the potential difference, then only there will be the flow of current. So with the application of the potential difference, proper potential difference, we can have the flow of electrons and the flow of holes in this conductor. So when you see to this diagram, here we see that the electrons will be attracted towards the positive terminal, and the holes whichever present in the conductor will move towards the negative terminal. So hence, as in the n-type there are large number of electrons, the majority current, what we say, are the more current flows only during the flow of electrons. The majority portion of the current in n-type semi-material is by the flow of free electrons. Hence, the electrons are called the majority charge carriers and the holes are the minority charge carriers. Second type of the semiconductor is a p-type semiconductor. This semiconductor is obtained by adding a trivalent impurity like boron, aluminum, indium and gallium into the pure semiconductor. These atoms, when added into the semiconductor, forms the covalent bonding with the germanium or you can say a semiconductor. So 3 of the valence electron of the impurity forms the covalent bonding with 3 of the semiconductor atoms. So one of them will be vacant and it needs an electron. It will be in the form of a hole as shown here in the picture. It will be in the form of a hole and it needs an electron to be filled. So this this gallium atom is said to be an acceptor atom due to with the addition of trivalent impurity, there will be one hole due to each impure atom. So apart from this, due to the thermal agitation, there will be a whole electron pair generated. So that also gives the holes that adds to the holes generated by these impurity atom. So hence there will be a large number of holes compared to the free electrons, and hence this type of semiconductor is called as p-type semiconductor. And the current conduction in this semiconductor is mainly due to the holes and not due to the electrons. When the potential difference is applied to the p-type semiconductor, the holes are shifted from one covalent bond to the another covalent bond. As the holes are positively charged, they are moved towards the negative terminal of the battery, constituting the pole current, and the valence electron, which are in minority, move towards the positive terminal, constituting the electron current. So here, as the holes are in majority, the current is mainly due to the holes, and the minority current is due to the electrons or the minority carriers. When a p-type semiconductor is suitably joined with an n-type semiconductor, the contact surface between these two is called as the p-n junction. The p-n junction is of very great importance as it will act as a control element for these semiconductor devices. The semiconductor devices, when you say as an example a diode, transistor or any of the semiconductor device, will be having one or more than one p-n junction. Hence, the study of p-n junction is very important. And now let's move into the p-n junction, its properties, characteristics, parameters and so on, essential to study all the semiconductor devices. What is a p-n junction and how it is formed? When this p-type semiconductor is suitable with an n-type semiconductor, it forms a p-n junction. So in an n-type, we see that these are the electrons. These are negatively charged, and here the holes are positively charged. When these two semiconductors are joined together, these free electrons will diffuse into recombine with the ends. All the electrons near to the junction jump into the hole and forms the bonding over there. Into the hole, here this atom will be depleted of electron and it will become positively charged. So the atoms here will become positively charged. And when we see to the p-type, when electrons combine with the hole, this elements or these atoms will be negatively charged. And further, when you see to this, the electron to the n-type cannot move into the p-type as these ions will reflect them. So there will be the repulsion and there is no further movement of electron. So as the electrons move across the junction, the p region loses as electron and holes, they recombine due to recombination. The result is that there is a layer of negative charge. So there will be the negative charge near the junction for the p-type and a positive charge on the n-type. And this region is called the depletion region. The name depletion is because this area is depleted of the carriers, depleted of the charge. There is a depletion of the charge carriers. So this region is called the depletion region. Previous slide we studied about the creation of p-n junction and the depletion region. So now let's go with the properties of the p-n junction. So once the p-n junction is formed, once the p-n junction is formed and the depletion layer is created, the diffusion of free electrons stops. So now the depletion region acts as a barrier to the further movement of the free electrons across the junction. The positive and negative charges, the positive and the negative charges set up an electric field. This electric field is the barrier to the free electrons in the n region, and there exists a potential difference across the depletion layer, and it is called the barrier potential V0. The barrier potential of the PN junction depends upon the several factors, including the type of semiconductor material, the amount of doping, and temperature. And the figure here shows the distribution curve of the potential, barrier potential. So here we see that at the junction the potential is 0. The barrier, as we move into the depletion region, the barrier potential increases. So this increase is positive because towards the N side there are positive charges. So the potential difference is positive, and into the N type the potential is constant. And when you go towards the P type, here the negative potential is across the depletion region. So the curve goes in the negative direction, and into the P type the voltage is constant. So this potential barrier is mentioned as V0, and this is the objection offered for the flow of electron into the P region. So the typical barrier potential is approximately 0.7 volts for silicon and 0.3 volts for germanium. To establish certain operating condition for an electronic device, we need to apply some potential that will overcome the barrier potential to have the flow of current. So in order to have this condition, we need to apply the voltages to the PN junction. The application of this DC voltage to the PN junction is called as biasing. So there are two types of biasing. One is the forward bias and the reverse biasing. So now let's study with the forward biasing and the reverse biasing of the PN junction. Forward biasing of the PN junction. In forward biasing, the negative terminal of this voltage source is connected to the N type, and the positive terminal is connected to the P type. The external DC voltage applied to the junction is in such a direction that it cancels the barrier potential. The barrier potential V0 will be reduced if we apply the external voltage. The battery pushes the holes and free electrons towards the junction. So if the potential barrier is reduced, the free electrons from N type will be pushed into the P type semiconductor. If the battery potential is less than the barrier potential, the free electrons do not have enough energy to get through the depletion region. When they enter the depletion region, the ions will push them back into the N region. Because of this, there is no current through the diode. When the DC voltage source is greater than this potential barrier, the battery again pushes the holes and the free electrons towards the junction. This time, the free electrons have enough energy to pass through the depletion region and recombine with the holes in the P type. So, these free electrons continuously enter into the region, right end of the diode, and holes are continuously moving towards the N type. This continuous movement of the free charge carriers will result in the current flow. As the potential barrier is very small, there will be a small forward current. As the voltage increases, the flow of electrons and holes also increases. So, when the junction is forward biased, there will be almost zero resistance offered for the flow of charge carriers, and this path will give a continuous flow of electrons and holes, which results in the current called the forward current. And the magnitude of the current flowing in the junction is depending upon the applied voltage and the density of the charge carriers. Forward current through a PN junction is due to the majority charge carriers produced by the impurity. Biasing of the PN junction. In reverse biasing, the P type is connected to the negative terminal of the battery and the N type is connected to the positive terminal of the battery. The external to the junction is in such a direction that the potential barrier is increased. So here the curve shows this. So this is with the application of no external voltage. This is the barrier potential due to the depletion region. So now when we apply the reverse bias voltage, the depletion region will have a larger potential for the flow of free electrons. So it is clear that applied reverse voltage establishes an electric field which acts in the same direction as the field due to the potential barrier. Therefore, the resultant field at the junction is strengthened and the barrier height is increased. The increased potential barrier prevents the flow of charge carriers across the junction. Thus, a high resistance path is established for the entire circuit and hence the current does not flow. The reverse current is only due to the minority charge carriers produced due to the breaking of some covalent bonding at room temperature. For the operation of the semiconductor device, the junction is to be present in the forward biased condition. So now let us see the current flow in the forward biased condition. We know that in forward bias, P type is connected to the positive terminal of the battery and N type connected to the negative terminal of the battery. So this applied voltage will be in the opposite direction to the depletion barrier potential. So that way this voltage will overcome the barrier potential. So in this case, now we can see that the electrons flows from the negative terminal of the battery into the N region as free electrons, and these free electrons move from the negative terminals towards the junction. So at the junction, they combine with the holes present in the valence band, and this propagate from one hole to the another hole in the valence region and enters into the positive terminal of the battery. This continuous flow of electron from negative towards the positive will constitute the electric current. Current is called as the forward current, and here we see that in the N region the current is carried by the free electrons, and in the P region it is carried by the holes. But in the external circuit, the current is carried by the electron flow from negative to positive terminal of the battery. For the PN junction, how it reacts to the external DC voltage. So now let us go with the volt ampere characteristics or the VI characteristics of the PN junction. So this volt ampere characteristics is the graphical representation of the applied voltage and the current in the junction. So in this characteristics we are going to study with both the forward biased PN junction and the reverse biased PN junction representation. So when you see to the VI characteristics curve, the forward voltage versus the forward current is plotted. In the same way, the reverse voltage and the reverse current is plotted. Okay. So now with the zero external voltage. So when the external voltage is zero, the circuit is open. So when you see to this, no application of voltage means circuit is open. The potential barrier is at the junction, does not allow the movement of the electrons and the hole. Hence there is no current flow at the external voltage equal to 0. So here both the voltage. So as we now move on with application of forward voltage. So when zero external voltage, at this point it has zero external voltage, the voltage is 0 and also the current is 0. Next we move to the forward biased curve. So when forward biased voltage is Vf and the current due to the forward biasing is If. So with the forward bias to the PN junction, that is the P type connected to the positive terminal and the N type connected to the negative terminal, and the potential barrier at this time will be reduced. The potential barrier here is going to be reduced. So there will be a small current flow. It starts give a flow of current. So at some forward voltage, that is 0.7 for silicon and 0.3 volts for germanium, at this forward voltage the potential barrier is altogether eliminated and current starts flowing in the circuit. Current starts flowing in the circuit from here onwards. So from this point known as the knee point. So we'll just see to that later. So after this point A, there is an increase of current with increase in forward voltage. This rising curve is obtained with the forward biasing of the PN junction. From the forward characteristics, it is seen that at the first, the current increases very slowly, O to A. There is small increase in current and the curve is non-linear. It is because the external applied voltage is used up in overcoming the potential barrier. However, once the external voltage exceeds the potential barrier, the PN junction behaves like an ordinary conductor. Therefore, the current rises very sharply with increase in external voltage. This curve A to the point over here, if you assume it may be a point B. So from A to B, it is going to be linearly increasing. Hence, the forward current there through the PN junction is due to the majority charge carriers produced by the impurity. So this is the forward characteristics curve of the PN junction. And now going into the reverse bias condition. So when the diode is when the junction is reversed biased, that is P type connected to the negative terminal and N-type connected to the positive terminal. The potential barrier biasing we have already studied, there will be the increase in potential barrier, and therefore the junction resistance becomes very high and practically no current flows through the circuit. However, a very small current due to the minority charge carriers flow through the junction, and this is depicted by the curve over here. So from O to the point over here till this point. So this current is due to the minority charge carriers. This minority current or little current is due to a few free electrons present in the p-type material and few holes in the n-type material. These free electrons and holes are called minority carriers, and the applied reverse bias appears as forward bias for these carriers. Hence, a small current flows in the reverse direction. If reverse voltage is further increased continuously, the kinetic energy of the electrons may become high enough to knock out the electrons from the semiconductor atoms. At this stage, breakdown of junction occurs, characterized by a sudden rise in the reverse current and a sudden fall in the barrier region resistance. This will destroy the junction permanently. This point is called as the breakdown. At this point, there will be a sudden rise in the current that will overheat the junction and break the junction. The reverse current is due to the minority charge carriers produced due to the breaking of some covalent bonds at room temperature. Points, whatever I discussed about the forward curve and the reverse biased curve. In the VI characteristics curve, I pointed you with the 2 points. One is the knee voltage and the breakdown voltage. So now let's see what is that knee voltage and breakdown voltage. First, we go with the breakdown voltage. So it is the minimum reverse voltage at which the PN junction breaks down with sudden rise in current. Under normal reverse voltage, a very little reverse current flows through a PN junction. If the reverse voltage attains a very high value, the junction may break down with sudden rise in reverse current. This breakdown is due to the electrons that acquire high energy, and they go and hit to the other electrons in the covalent bond. That hitting will release one more electron, and that electron with higher energy will hit the other covalent bonding, and so on. There will be a release of large number of electrons. This release of electron due to the breaking of covalent bond is called as the avalanche breakdown. This breakdown results in large number of electrons that in turn will give a large reverse current with the high voltage. So when this is increased beyond this with the higher current, there will be a breakdown of the junction. Hence, it is called a breakdown voltage at that point where the breakdown of junction occurs. Next is the knee voltage. It is the forward voltage at which the current through the junction start to increase rapidly. So when you see to the curve over here, from 0 to a 0.7 voltage, there is a small increase in current, and later after some point 0.7, there is a sudden rise in the current, and this is called as the knee voltage. So for silicon it is 0.7 and for germanium it is 0.3. So till the voltage 0 to 0.7 is required to overcome the potential barrier for the free electrons. So once this 0.7 is reached, there will be a sudden flow of electrons and there will be the breakdown of barrier so that the electrons flow with higher current production. This is in the forward biasing of the PN junction. In this video, we have studied about the semiconductor, the types of semiconductor, PN junction formation, its biasing, VI characteristics of the junction and the limiting conditions of the PN junction. So the rest of the part for the module 1 we are going to study in the subsequent videos. Hope you understood the concept. Please like and subscribe for my channel. If you wish to get the full explanation with the numerical analysis and the examples, you may get the online tutorial classes. So that you may inquire on my email mentioned in the slide below. Thank you.